Anyway, so we had like a JSON-RPC spec introduction in fundamentals. We just like touched like the general concepts and why the new spec was better and all of that. But this one is actually how do we get to interact with the JSON-RPC server, okay? So first, like a bit of a recap of like some concepts just to put everything into place. First is like about the block states, right? So remember that we have something which is called the finalization and so on. So we have a block which is the finalized one, and everything that's behind it is like all of the finalized blocks, yeah? And then we can have like multiple forks and stuff with the new blocks that are coming through. And one of these branches, one of these forks will be the best block. And then all the branches that fall behind and that weren't finalized, then they are what we call pruned. This is something that we like. Fork and pruned is like something I put here. It's not an official language, but best and finalized, it's all over the place. Yeah. Also, a recap on JSON-RPC, like really quickly. JSON-RPC is just like this standard of like sending messages between a client and a server. So when you want to make a request, you pass, well, the header and then an ID with a method and all of the parameters. The ID, remember that it can be a string or a number or no, actually. And then you get the backend response with the result in it. And there's also like another concept, which is like a request, but that you don't expect a response. And then you can just omit the ID. And this way you can send notifications. We saw this in the thing. And then we have like the JSON-RPC spec, which is now from Polkadot that, it's like this new thing that defines, how essentially dApps can interact with nodes. And there's this very important concept, which is group of functions. So all of the functions defined by the RPC spec are grouped into this group of functions. So we have RPC, chain spec, chain head, transaction, watch, archive. We also have like pseudo something. And the idea behind this is that a node can choose which one of these they can implement. But if they choose to implement one of these groups, then they need to implement all of the functions within that group. Okay, so this way you can know the capabilities of this node. So if you connect to a small dot will tell you, I support RPC, chain spec, chain head, transaction, watch, but I do not support archive because the light client doesn't have archive functionality. And then your dApp can, see this and say like, okay, then, I will not show like old blocks. I will only show information for the current blocks or whatever, right? Like you connect to the chain and then you're gonna get that. So yeah, on this particular session, we will focus on chain head. Question?
Is it possible to only have a child of a function to be called to the JSON-RPC, or do you have to call the whole group of that function to be able to call like a nested sub?
No. When you make a call, you just can call one of the functions inside the group, right? Like the group only says that the node has to implement all of the functions inside that group. So yeah.
So they can't choose like one function in a group at all. It's like they have to have the chain head dot function inside of the chain head, or is there a function inside of chain head? Or?
Maybe I'm not understanding the question, but I think that yeah.
So this is a good question. This is explained if you go to the doc of the new JSON-RPC spec, it explains why the group of functions and why it's all or nothing. It basically has to do with node capabilities, right? So, for instance, a small dot obviously cannot implement archive, right? Therefore, none of the archive functionalities are there. But it also explains why it wouldn't make sense for a node to kind of pick a group of functions, but not implement certain things, right? Because then it becomes very, very difficult for consumers of the like tools and stuff to actually make sane assumptions, right? So does that make sense? So it's basically all or nothing. Sorry, is that what you're asking, or?
I don't know. It's defined for the spec. So the spec defines that nodes have to implement that or nothing. Yeah. It's not how it turned out. It's just like if you look at the spec, it actually says that this is a requirement. But then yeah. So as I was saying on like this session, we will just focus on chain head. Like the other ones, like chain spec and RPC, like are too simple. And tomorrow we will look into transaction. Okay. So this is just like one example of like the RPC group only has one function, which is called methods. So you call RPC methods, just like passing a request. I pass ID1, RPC methods, takes no parameters. And then the result, it comes back with an array of all of the functions that this node supports. And here you could ask like, well, why don't we have like one that is just like, if it's all of nothing, why don't it just say I support chain spec, chain head, and so on? It specifies each one of these. And well, the answer to that is that these RPC methods was a function from the legacy API, and it was reused for compatibility reasons. So and essentially, like it was just a way of reusing it, and it's just redundant information that you get, but that's fine. But you can assume that if you get like chain spec v1 chain name, then you will have the other ones. Yeah. So going into chain head. So we will take a look at the functions, but I've grouped them up into like 3 separate subgroups in terms of like the role that they take. Okay, this is not something official. This is not something in the docs, but I think that it makes sense, and it's a bit easier to follow them. So there's a group that deals with subscriptions. Well, first of all, like the chain head group of functions, it's used to follow the chain head. So it's like get the receive new blocks, and as they come through, and then you get like events of like this block is finalized, and you have this new block, and so on. And also like request, for storage called data and all of that. So the first group that I said deals with the subscription of part. So we have 2 functions. One is called follow, and the other one is follow. So follow is like you start the chain head subscription, then you will start receiving events. And when you're done with that, you can call unfollow. And that concludes the stuff. Then we have another group, which I call operations, which is to query information. So there's chain head v1 header to request the header of a block. There's chain head v1 body to request the body of the block. So this is all of the transactions within a block. Then you have chain head v1 storage, which this is a bit more interesting because now you can query storage by key of a specific block as well. And call is not transactions. Call is runtime APIs. So you can say like, okay, I want to run a runtime API on this block that has this name and these parameters, and then the node will run it and give the result back to you. And lastly, we have another group which I call like control, which is it's like to manage the state or like of I don't know of the subscription itself, right? So we have chain head v1 continue, and this we will see it later. But essentially, like when you do a storage query, if it's too big, the node can tell you, hey, I'm giving you a list of like, I don't know, like 100,000 entries, but if you want more, you have to tell me if you want to continue on that. So now you can call this to say like, yeah, continue this operation, like give me more results. We have stop operation, which is each one of these operations, you can just cancel it. So imagine that you make a runtime call that takes like a lot of resources, and the user is like, okay, no, I just don't want this anymore. Then you can do stop operation and cancel that operation. And lastly, unpin. And this is for block pinning. This is like a complete like separate thing. I don't want to make it too complex here. We will talk about block pinning later. Yeah. So far, so good. So let's take a look at the first function then. It's called chain head v1 follow. This is like to start the subscription. You cannot do any other function before you do this one. Okay, so like this is the first one because you need to start the subscription. So it takes one parameter which is called with runtime, and pro tip, always use true. Okay, we will see later why this is, but so what with runtime does is it tells the node that you want to do something with the runtime, with this subscription. But if you think about it, you need to do something with the runtime on every single thing. Like if you want to query storage, well, you need the runtime because you need to know how to decode that storage. If you want to make a call, you need the runtime. So, yeah, there's this parameter that you can put true or false, but pro tip always is true. False is like not very useful. We will later we will see an example on how that works. Then when we call this, what we get back is a subscription ID. It's just like a random string. You know, doesn't mean anything. You cannot decode this. It's just like a random string which says like, okay, I have created a subscription for you, and the idea of this subscription is this one. And now the idea is that the node can send us notifications as if we were a server, actually, right? Like remember on the JSON-RPC spec, right? It's just like a client to a server, and the client always sends requests and notifications to the server. But on that session, we mentioned that we still can use the JSON-RPC spec so that the server sends notifications back to us. So it's a bit of an abuse because that's, but you can think of it as like, okay, now we take the role of a server, and now the node can send us notifications, which is chainhead v1 follow event, but this is just the name of notification. And then inside we have a subscription, which is the same ID that we had. So now we can know, okay, this follow subscription is tied to this one. And then the result, it's a bit of a bad name maybe, but the result is actually the event that we're getting back. Yeah. So what are these events? So now, from now on, like these objects, like these things that I put here, you have to imagine that they come inside that result. Okay, so they are nested inside there, but it's just to see what we have. So if we try this, what we will get back first is like initialized. So initialized, it's like the first event. We only receive this event once per every subscription, and it just tells us like the starting picture, right? It tells us, look, like the list of finalized blocks is this one. The last blocks that I know are these ones. And then also like give some information about the runtime, like the version of the runtime and all of that. Of course, like this only comes if you have put with runtime true. If you put it with runtime false, you don't have the runtime, so it's not there. But anyway. Then when a new block comes, you have another event, which is new block. A new block always has like its own block hash and then the parent block hash. Because remember that you can have multiple forks and so on. So you need a way of like saying, okay, this block belongs to this parent and so on. And if this block had a new runtime, you have a runtime upgrade, then you have a new runtime here. If not, then this is completed. Then we have another event, which is best block change. And this tells you when the best block pointer changes to a different one. Like, remember the picture, right? We have the finalized block, then we have all of the forks. And one of these forks is the best block. So when the best block changes, it changes to another block hash, and you have an event. And I think this is the last one. This is a finalized. And this tells you when a new finalized block has become finalized. Yeah. So you have, well, why don't we have just one finalized block here? Why do we have like finalized block hashes? If finalized is just like moving and it's like telling, okay, now this is finalized, this is finalized, this is finalized, why would have a list of finalized block hashes?
I think because the finalization on Polkadot can be multiple block being finalized.
Exactly. Yeah. it could happen perfectly that we have a finalized block, then we have like a long list of blocks, and at some point, like grandpa, mix his shit together and says like, oh, like all of these blocks are now finalized. And so you have like all of those blocks coming through finalized block hashes. And then we have another group, which is pruned block hashes, which is like, it just informs us like, like these blocks that I said before, they can no longer be finalized. So they are pruned, they are removed from the chain. Yeah, so this is like a bit of, just to explain this, right? Like, imagine that we had the finalized back here, yeah? And now we receive a new finalized event of these two blocks, then we will have two block hashes, this one and this one. And then this will become pruned. So it will be pruned block hashes, these ones, right? And same thing with the best, we can change the one for the other and so on. What I think we can do now, before we move into block pinning, is see a demo of this. So for this, I'm back on the repo we're starting, and we will make this bigger. Space. Okay, so instead of using a web socket, I'll try to use small dot instead. Small dot start. Small dot change spec to import this, and I need to import this change spec from. I'll do Polkadot because in theory Polkadot should be faster. Polkadot API change Polkadot. There it is. Okay, and now I can come here and do get small dot provider of this chain, and I will remove the. Anyway. Okay, so I created a new client with a small dot and so on. Now, there's another thing we can do to make this a bit easier to see, because if you think about it, like small dot is running in the same browser. So if we run this and take a look, npm dev. So here's small dot is doing its own thing, but if we go to the network tab, oh, this is like too big. Okay, now. So I will actually refresh it, but you can see like there's like all of these static files. But then we have these ones, which is like, oh, these are WebSockets. What are these WebSockets? And it's like, oh, it's all binary message. I cannot read this, right? Where is the JSON-RPC connection with small dot? Right, it's not here because like small dot is running inside the browser, so it's not connecting to, all of the messages, like all of the JSON-RPC messages are happening, but they are not going through a network interface. They are just going, from the JavaScript runtime into the worker of the bosom of small dot. So all of these connections is actually small dot connecting to peers and asking for proofs and all of that, but we're not getting any message back. So what we can do here is take advantage of our. So if we come here, of the JSON-RPC. So we can take advantage of like this interface to put like sort of like a middleware that logs the messages that are being sent and received, right? So I'll come here and say like I need this, and actually I will not even create a client for this because we're gonna go full low level here. But well, just to put the example, so you would do just like create client, and I want to see the messages that are being sent and received. Then you can do with logs recorder is how we call this thing, and then now you can pass in how you want to persist the log. So if you're in a server, you can like put it in a file or whatever. Here I'm just gonna console log this. And now you can see that the input is another JSON-RPC provider. So this will act as sort of like as a middleman between one and the other. Maybe later we can try and implement it by ourselves. It's not that complicated. So now that I've done this, you can see that now we see all of the messages that are being sent and received. So first we send a chain head follow, and we get back a subscription ID. We get back a subscription ID, and now small dot has connected with its peers and so on, and then we receive all of the events. What I want to do though is not use the client because otherwise, like we have so many stuff getting through. So I'll just get the provider. This is our provider, and now we can take a look at this interface. Actually, I think it's a good idea if we wait. I'll make a commit first if anyone wants to have like this code. It's like extremely simple anyway. So I think it can be a good idea just to see like how this interface works to create the with log recorder by yourselves. Okay, it's extremely simple, believe me. So here we have like our small dot provider. It's essentially like the one that talks with a small dot, and now this is a bit more complex because you have to work a bit with small dot internals and so on, but this is fine. What we want to do is like just create a new JSON-RPC provider that uses this one, but that logs the messages. Yes. So I'm going to call this just provider, and to get some help from TypeScript, I'm going to say that this is a JSON-RPC provider, and it's not importing it, but I can import it here. Oh, JSON-RPC. No, we are exporting it from website provider, and this is just like the type I want to import. Okay, now, so this way we can see that this is a function. So it's a function that receives one parameter that's called onMessage, okay, onMessage. And what it's telling us is that it needs to return a value, which has to be a JSON-RPC connection. Okay, let's return a value. And now we can see that this value needs to have two methods, connect, disconnect, and send. So I'll do send and disconnect. So now this provider is already TypeScript compliant. It's like we read this quickly just because of like ESLint, it's telling us that it's not being used and whatever. But now this is spec compliant. Okay, so we could actually pass this to Puppy, and Puppy will just do nothing with it because it does nothing. But now what we can do is like use a small dot provider to connect this small dot provider. So to connect with small dot. So what we can do here is like, okay, when someone calls our function is to start the connection. So here I'm going to create like a small dot connection. And this is a small dot provider. And a small dot provider takes an onMessage. So if I want to do what's called an identity thing, which is like just do the same thing, I would just pass it in onMessage. And then here I would do send message. So, and disconnect. So with this, I'm saying like, okay, my provider is just like creating a small dot connection. And when a small dot receives a message, just pass it down to Puppy. And when Puppy wants to send a message, just pass it down to small dot. Yeah. But now we want to log these messages. So what I can do here is when I have a message, when I have a message, okay, I will pass the message back to Puppy, but I will also log that we have received So I can do this, and maybe I can actually like put it all in string this way. Date now, so this way I can have like a format of like, hey, I'm receiving at this timestamp this message. I could do that, yeah. And now when we're sending a message, I can do I'm sending on this timestamp this message. Okay, so this should actually work, and I can try it. I will not use this because what I can do is like, okay, now my connection is provider, and then when I get a message, I'll do something with it. And then if I do this, nothing will happen because I didn't send any message, right? So small.dot is now waiting of like, hey, what do you want? Like, give me a request. So I have to send a request, so I can do connection.send, and here I have to pass a message. But look at this message has to be a string because like JSON-RPC works with strings. So I have to JSON stringify. And now this is this thing of like, okay, I need to put the header. So JSON-RPC 2.0, ID, I'm going to use 0. And now, I don't know by heart. I need to look here. But yeah, I'll just like copy and paste this thing. Like I'll just send a follow request, method follow of params true. And now that I have saved and this has reloaded, we can see that now stuff is happening. Yeah. So we are sending the follow subscription, and small.dot comes up back with this token. And now here we see all of the events coming through. Yeah. So we have follow event of initialized and with all of the finalized block hashes and so on. And now here we have another follow event where it's a new block, and this is the block. And now the best block has changed, and the best block is this 743, which is just the block we had here. And here you can see every block that we had. Like so, another new block, the best block changed, new block. Let's see if we find a finalized. Here it's a finalized. So here we have like a finalized event where the finalized block hashes, it's just one, which is this one, and we don't have any current block hashes. Okay, so this continues for this one. Questions? Yeah. I'll push this. More questions? This one.
Is there a lifetime for each chainhead subscription ID?
A lifetime? What do you mean?
Like, if I have the JSON subscription ID, does it just last until there's no more clients using it, or does it ever become invalid?
At some point, it might become invalid, and we will run into this. But theoretically, it can run forever. Okay, but there are some conditions that it can cause this subscription to become invalid, and then you have to start a new one. Yeah, like just in a few more slides, we will be there. Yeah,
I'm not skipping ahead. Don't worry.
That's a good question. So, is it? Remember about that unpin method that we had before, and I said like, don't worry about this, it's a bit complicated, so on. This has to do with block pinning. Okay, so let's go into this. Like, if you remember the JSON-RPC spec, one of the actors that is like trying to cater to is the live client. The live client has like limited resources, right? So we need a way of letting the live client know, there are some blocks that you can now get rid of because we will not need them anymore. So this is where the block pinning concepts come. Okay, what block pinning says is that every single block that the node gives you is automatically pinned. So pinned means that the node cannot just get rid of it. Okay, and now it's the responsibility of the client, of the dApp essentially, to say like, okay, this block that you have given me, I'm not interested in it. You can discard it if you want. Yeah. So every initialized event that we receive, we have like this list of finalized block hashes, right? So we have like the initial picture of like, this is the block hashes. All of those blocks are pinned because it's blocks that the node has given to you. And so, if you don't dispose them, they are kept in memory. And every new block event also has a block hash, and that block is pinned by default. So now there's a question of like, what happens if you just don't unpin any block? The memory gets big, and at some point the process would crash, right? Because like, again, like, well, maybe a full node doesn't care because a full node already has so many blocks there and doesn't care. But the live client is like running in a limited environment. So, at some point you will get a notification which is called stop. And what this notification means, it's an event of like the follow, as if it was like a new block hash or whatever. But stop, what means is like, I'm running out of resources. You are keeping like block spin that you should not have. So I'm stopping the subscription, right? And then all of the blocks become unpinned by default, and you will not receive any other event on that subscription. So in that case is when you have to say like, oh, okay, I'm a bad actor. I'm really sorry. I will start another one. So actually, if we come back here, exactly. So because what I did on this example is just like send a follow event and do nothing. The node has been sending us like new events and finalize and new events and finalize and so on. And at some point it was like, you're not unpinning anything. So I'm stopping you see like there's like event stop. I'm covering here. But like we had one last event, which was this subscription is event stop. And now I'm not receiving anything else. Yeah, we're not banned. Like it's okay. Like you can start a new subscription if you want, right? And then you will receive like new blocks. But this subscription is completely dead. Now, event stop. It's not the only. It's not only for block pinning and so on. So event stop is just like, okay, this subscription has to die. What's another case where a subscription has to die? So imagine that, you're connected to the chain, you're receiving blocks and all of that. And at some point, your internet goes down, right? If your internet goes down, small dot or whatever node essentially cannot get any new blocks, right? So you will not receive any event. If the connection comes back up, like quite immediately, small dot maybe can, talk with peers and say like, hey, I was disconnected for a while, give me like the latest blocks and so on, and it will hopefully like, keep the chain alive. So essentially it will detect all of the blocks that have happened between the disconnection and so on, and it will just give them to you, okay. But if when it reconnects, it cannot find some of the blocks that were in between, then we have a problem, because when you have like a new block, you're given a parent block hash, right? And this parent block hash, you're guaranteed to have it seen. But by the spec, you cannot have one event which is like, hey, here's a new block, and the parent block hash is a block that I have not told you. You have not seen this block. This cannot happen, right? So if small dot at some point has like a gap of blocks that it cannot see, then it cannot give you more events, right? So it will tell you stop. And it doesn't mean that you have done anything wrong. Essentially, you lost the connection or whatever. And if you receive a stop, it's like, okay, then I have to reconnect, and then you will get a new initialized event with a new list of blocks and so on. Yeah. With this, I also want to show another thing is like, okay, what happens if I put false here? So I do a follow, but I say I don't need the runtime. because like for this demo, for instance, I didn't need the runtime, right? It's just like, okay, give me the block. So in theory, this should make it faster because in this way, like we're telling Small.k, we don't need the runtime, so you don't need to compile it, you don't need to download it. As soon as you get blocks, just give them to me, and this way I will be faster and so on. So I'll save this. And by the way, what I will do here is the log, my log provider thing, instead of like doing a string, I'll do actually JSON parse the message, because this way I can explore and it's a bit easier to see, I think.
I have a question about the WebSocket debugging. Usually in the network, if you go into your Chrome inspector and you go on the network tab, there is like a dedicated socket area to look at WebSocket messages.
Yes.
So maybe I missed it before, but like this, when you use small.dat, like you kind of bypass that. Like, do you lose the opportunity to use that Chrome inspector tool?
No, so the thing is that the small.dat is running inside their browser. Right? Like there's no, like small.dat is not listening to any port or whatever. It's not using a network to communicate with you. So the way it works is like there's like a window post message where you can like send messages to small.dat back and forth.
Yeah, but like he's asking like if you because of that, like debugging is harder basically because you cannot go to Chrome and inspect it. Which the answer is yes and no. It's not as convenient, but like we have put like because our JSON because our JSON provider is so minimal, we have created like this with logs that it allows you to basically split the logs in whichever you want. It could be a terminal, it could be anywhere you want. And not only that, we also have a provider that is, maybe I'm getting ahead of myself and you're going to explain that later. But we also have a provider that can instantiate a client from the logs that you have recorded in case that you need to debug something. So basically, like, so we have like, it's in the docs, but we have like with logs recorded, and you can split it in the console, you can split it in a file, you can split it in 2 different places, you can split it wherever you want in a UI visualizer, whatever you want. But if you put it in some file, then later you can create a provider, not from small.dat, not from WebSocket, but from a file with logs. And then you can that's what we do when we detect like there's a bug, like we use the with logs recorder and we
It's like you're replaying the
exactly
events. Okay.
and yeah. So
Okay.
so yes, you're right. Like you don't have the convenience of going to Chrome, but
This, right? Like
exactly.
Okay.
But you can, but basically you can work around that by just like basically putting in a file and doing tail and then looking there basically. You know what I mean?
Yeah. Okay. Thank you. Sorry for that. Thank you.
Yeah. Please come back later. Now it's back. Yay. Okay, so it works. So what Josep mentioned is that this with logs recorder, you can see that it's actually a logs provider. So there's actually here something called logs provider. And the idea with this is that with logs recorder, you can, so remember that when I use with logs recorder, you know, like recorded is with logs recorder. And I did this console log and small.provider, right? When I did this, it's like, oh, I just want to console log the messages. What you can do with this is like, no, I want to store these messages in a file. And then once you have those messages in a file, then you can actually remove essentially small.dat. So imagine that you find a bug or whatever. You can just remove a small.dat and say, now my server is a logs provider of these logs that I have recorded before, right? And now this, I know that it sounds like, oh, this is amazing. It has a few caveats, like when you get to work with it. but essentially, like in here, you would pass in the logs that you have recorded before with the logs recorder, and now it will replay the same messages as it had like seen it, right? Now, the problem that this has, like if you ever try to use it, most of the times it works really well, but some of the times it's a bit hard because it expects that all of the messages come in the same order, right? Like that the client, essentially the dApp, is making the request in the exact same order as they come through because it's not a Polkadot node by itself. It just like repeats the logs as they come through, right? And all of that. So it's a bit tricky sometimes. But anyway. So yeah, what I was explaining is like I just changed this so that I get like the log into an object so I can see it better. And now here on my connection, I'm sending a follow with runtime false, okay? Because I want to have the things fast. So now what will happen here? Sorry, I have to remove this. So I have sent my follow event with params false, and Smallnet is like, sure, there's this thing here. And if we actually refresh it, you will see that we immediately receive a follow event of like, hey, like here's initialized with this block, which is like, whoa, this is like, it went extremely fast, right? Like we didn't even need to wait for Smallnet to connect to peers. Like we already have a block. But what happens next? Stop. And it's like, why are we receiving a stop now? Anyone can guess? Like what happened here is like, okay, I just like submitted, like I'm subscribing, and I get like initialized with a block and stop. I don't receive anything else.
Is that some like kind of cached block that we receive when we connect?
Yeah.
The old one.
Yeah, exactly. So remember, like when we pass the chain spec to a small dot, we have there's the lightsync state, right? And that lightsync state has like some information. One of them is like the last block that was essentially recorded when that happened, or I think it's the one that that changed the validator set and so on. So that's a block that the small dot has and knows that this block is trusted. So it's like, yeah, like here's your block that you have asked, is this one. But now a small dot is starting to connect with the peers. Right? When I do this, you see like I receive the block immediately because it's cached. But now a small dot is like connecting with the peers and asking for blocks. And at some point it's like, oh, like, okay, now I have the runtime ready, but I have it for a block that I cannot trace back to the parent. So here I have given you a follow event with initialized, but now I have like a new block that it's not related at all to this block. So I cannot give you essentially a connection to that, right? So now what we can do here is so when we receive, so I'm going to parse this message, right? So this is the message that we got from Smallnet. So parse message, it's JSON parse message, and I want to do if the parse message dot method is follow event. And the parse message dot, let's see, dot params dot result dot event is stop. Params result event. Params result event is stop. What I will do is send a new follow subscription. So this, I'm going to put this in a function so I can reuse it. Const function send follow. So I can have this thing here, and I will call it so that it will start like with a follow subscription. But now another thing that I have to do is that this ID has to be an identifier. Like I cannot repeat IDs for the same connection. So I'm just gonna put like a number. So I start with ID 0, and then every single time I'm just like sending that ID and incrementing by 1. Right? Like hopefully you're familiar with this syntax. And then here, if I receive a stop, I do another send follow. So note that I'm doing send follow with false again, right? So I'm sending follow with false. I get this event. So I send follow, and we got the event. This was like the stop event of like the initial one, right? Because like we got like the initialized with this block. Now small has connected, and we don't have continuity, so we got stop. And when I receive this event, I send again a new follow with runtime false. Right? I have not changed this, but now you can see that small dot can give us an initialize, and then all of the events. So there's an initialized, then new block, and then will be best block changed, and so on. See that? And now the difference that we have with this param false is that when there's a runtime upgrade, we will receive the block immediately. It will not wait to download the runtime before it gives us to us, which it would be faster. The only thing is that we usually don't care about this, right? So this is why I said, like, pro tip, always use true, because first, like, you avoid this initial issue of like, okay, I'm putting like a false, and now I'm getting a stop, and I have to resubscribe again. But really, we don't need it. By the way, what's important to notice is that even though if I put true into these parameters, now we receive this, and now small dot is doing its own thing before we receive the message. It could still happen that we receive initialize event and then stop. Right? Like we don't have any guarantee that by putting through this will not happen. It could happen perfectly. Like imagine that we start small dot starts connecting with some peers, and these peers are like a little bit behind for some reason, and now it's getting information that's outdated, right? So at some point it will give us an initialize, but then as it talks with new nodes, and new nodes are like, no, like these guys are like not updated or whatever. Like those guys are essentially dead. The new thing is here, and here's the proof for that. Now, the small dot could say like, okay, I do have a runtime and it's compiled, and I have given you like initialized event, but now I have new peers that is like, no, the chain is up there, so I cannot give you continuity, so you will receive a stop. Yeah. Any question so far? Otherwise, I would say like let's take a 5-minute break just to clear up. Okay. That's okay, and we'll continue later.
I'll continue.
So to be clear, oh god, I think does it connect to other nodes, and then the light client collects to like the closest nodes? I don't know why. Yeah.
No. Like if you look at the network lab, you will see that there are like there are like dozen connections that people are doing. Yes. They were all binary messages. So those messages were small small link on P2P essentially with those nodes and this information to verify blocks and all of that. But it doesn't trust just one, right? Like it would be like
whichever information majority or okay.
the only thing is that it's all trustless, right? Like it's not that I'm getting information from this one, so let's see if the other nodes give me this information. Like it doesn't mean that. What it does is like so like with the grandpa proof and all of that, right? So it receives blocks. These blocks are not trustable, so it's like I can't really trust this block. But then instead of like waiting for another block, what it does like it has another node of like a proof of this block. Right, and then with the proof, it can trustlessly say like, okay, then this block actually makes sense. Now this block is
Those aren't your timestamps, those are timestamps of the event. Like, or no, they're your. We say date now.
That's cool. Maybe when we come back, I'll explain it also for everyone. Yeah, so it's an important thing.
To have like your answer that like once you have up with the law, right? Then you right? And you see, and then you have these probabilities like make it go 50 times faster.
Oh, okay.
Maybe something like that way you
That makes sense.
that in a way.
There's no latency here, it'll lag.
So sometimes it takes like 5 minutes.
Yeah.
is it something common that now everyone is like trying to like, or like if you can figure it out and you put it into configurations, then people be impressed, I think. So I was like, so, I mean, I don't know, like when you're investing in whatever, when you're at a API, but not everything. Like when you talk about it, like, oh, if the API is at 1%, then it's not even covering the application cost. So maybe I do like could do it, but yeah. It's not just hard because like you don't have to come from your country, right? And you have like different consider different mix. Because you're one of the things that if you're it, then like what do you do? But it wasn't a type of
Okay. Let's continue. So during this break, I had one question from someone, which I think that we can just recap a bit on this, right? So remember that this is like from the first day, I think, on the getting started with Polkadot, that we have like two different branches. Like we can choose to go with a small dot, or we can choose with a WebSocket provider, right? Like the stuff that we see in the network tab is these two arrows right here, right? So if we do a WebSocket provider, this goes through a JSON-RPC connection. So it's like string messages with all of the JSON-RPC messages with a node. So we can see on the network tab, yeah? But if we use the small dot provider, then the light client, small dot, is running inside our browser. So the JSON-RPC connection is this one. Like this is the string messages that are passing through, but it's going through the window post message interface of the browser, right? So this is why we don't see it in here. But what we see is a small dot connecting with peers through libp2p. So it's using a binary interface to see that, right? So if I go back to this and go to the network app, and yeah, I can filter by WebSocket. Socket. So all of these connections that we see here is small dot connecting to every node, like, well, not every node, but multiple nodes in the chain to, get blocks and verify proofs and all of that. And if we inspect them, they are not JSON-RPC, they are actually binary messages. Right? It's like something we cannot decode by hand because this is a libp2p. Yeah. And now the question is like, what is Small.dot doing with all of this? Well, like essentially, like it's receiving the blocks, but all of these connections are trustless, right? So Small.dot doesn't trust absolutely anyone. At some point, I made a contribution to Small.dot, and I got like a review from Tomaka with I don't know how many comments telling me like, hey, you're getting this information, and this information is not trusted. Like you need to verify it, right? And you need to get the proof. So you need to talk with other nodes for these nodes to get you the proof that then you can build it yourself and verify that the block that you're working with, like the information you're working with, is actually true. And then when it's true, I can reply it back to the client, like to the dApp, right? So Light Client is doing all of these verifications with every node, and once it verifies that that's true, then it tells a Small.dot provider, hey, yeah, this is a new block, right? And now we can trust this block. Yeah. Did I commit the? I don't think I committed this. This is follow after start. Okay, so now we're going into operations. So remember that please. So remember that we had, we now have followed the event, and now we're receiving event. So we now made the follow subscription, and we're receiving events from the node. But if we want to do like a storage request and whatever, like now we need to do operations. So this is a sort of like querying, right? So the idea in general is that you send an operation request. So you say like, hey, I want the body for this. And what you receive back is not the body directly, because Small.dot doesn't have the body. So what you get back is an operation ID, which tells you like, sure, I'll work on getting the body for you. Here's an operation ID, so that you get to know when I have it. And after some time, you will receive another follow event. So you don't have to do anything. You don't need to do polling. You just receive an event with the operation ID and with the result. Yeah. Now, this is like the general thing, but there's one exception that, because we like exceptions. So the exception is header. So if you do header, you ask for the header with this follow subscription of this specific block. And what you get back is directly the result. Why is that? Well, because the header is always there, right? Like every node that is working with the blockchain, if it's a full node, if it's an archive node, or if it's a light client, they all have the header information of all of the blocks, right? Like the minimum thing that you have is like a light client that all it does is like synchronize the headers. So the header is always there. It doesn't need to fetch or anything. So this is why it just gives it back straight away. But then for the body is what I mentioned. So you make a request of change head body, follow subscription, and for this specific block. And what you get back is an operation ID. Yeah. And after a while, like now the node is like looking at the database or whatever, or talking with other nodes to get this body. And when you have it, then you have operation body done of this operation ID. So you can see that, okay, this body that I have requested for this block is this one. And now you have the value. Yeah, and the value of body is each one of the transactions of that block. So there's, I have an exercise now for you. Correlating JSON-RPC spec operations. So I don't know if you see a pattern here, but it's something that it's quite tricky when you work with messages and so on. So like you have a WebSocket connection, right? And this WebSocket connection is bidirectional, and in the same WebSocket connection, you're sending messages, you're receiving responses, and usually, I'm sending like a request of ID1, and I get back the response of this ID1. So I can correlate that, the message I sent in here, I'm getting back a response, and this response, I can match it with the request I made, right? But now, if you look at this, it's more tricky because in here, I'm sending a request of ID1, but this needs another ID, which is a subscription ID. Sorry, the follow ID, follow subscription ID. Yeah. So first, I send the follow subscription, and the follow subscription gave me a subscription ID. And now, when I want to make a request body, I send the follow subscription ID and the request ID, and I get back a response of this message with an operation ID, right? And later, the server will come back with, like, remember that this event is inside a bigger message, which is a notification. And that notification has the follow ID, and the event is an operation body done of this operation ID, right? And this is all happening inside the same WebSocket connection. As developers, like as client developers, we're used, I don't know, to the fetch API, which is really simple, right? So it's like, I want to request something, so I'm going to send a fetch request to that, and then this gives me a promise, and the promise is resolved with whatever value I want. And then I can send like 5 fetch requests, and I get 5 promises, and they will resolve as they come. But this is a bit more hard because we're dealing with a WebSocket and all of these IDs that I have to mix and match. Yeah. So my idea here is for you to try and correlate just one message. Okay. So what I'm gonna do is come back here, and we'll try to more or less make the skeleton of this so that you can just pull it and you give it a try on how to work with that, okay? So I'll do a send follow with true, and I don't actually need this. Well, in case that you get like a stop event, that's fine. So, okay, I got like, I think that this provider, we can leave it so you can see like the messages coming back and forth. This is fine. Now, I'm setting this ID because as you need to send messages back and forth, you will need something that increments, right? Because the IDs have to be unique. So just use sort of like this pattern when you want to send a message of like, okay, I'm sending just this ID and I'm getting it back. And so let's see how this works. The idea is I need to implement a function which is get body for one specific block hash. Okay, and this is to be done. So in theory here, you will do something like connection.send, and you will have to send a request that I'm not really sure what it's going to be now. And then here, remember that the messages, you're receiving them here, right? So in here you have your connection, and here you're receiving all of the messages that are coming from the node, from the light client or small or whatever, right? So this is, for instance, a small telling us there was a follow event, and this follow event was a stop. So in this case, we send a follow message again. But in here, you would have something like, I'm not really sure how much I should show to you. Right? So that's the thing, right? So I send like a chain head v1 follow, right? And now I will receive here something that tells me like, okay, your follow subscription is this one, right? So at some point they will have like follow subscription, figure out follow subscription, figure out follow subscription, yeah? And now when I want to send a new body, I need the follow subscription inside here, but I received it in here. So you will have to find a way of like, making this to communicate. You can use like whatever you want, like global variables or whatever, like it's fine. But in here, you need the follow subscription in here. So you will see that you have to do some sort of communication between what's happening inside here and what's happening inside here, because from here you are sending the message, and from here you're receiving the messages. So yeah, there's a bit of back and forth. Yeah. So yeah, I'll give like 45 minutes, I think, like up to the break, because this is a bit of a long exercise, but for me it's interesting, like to see how to correlate messages. I think it's something that's quite important. So I'll commit this. Okay, and give it a go. And then we will put it together after the break. Yeah, back on this. So like this is a function that anyone can call, right, to get a body for a specific block hash. Now, what is this block hash? Because I had a couple of people asking me. Well, it's one of the hashes of the blocks that you have received. Yeah. So this is now up to the consumer. So essentially, like the thing is, I don't want to make it too complex of like get like the list of blocks and all of that, because otherwise this would get too long. So imagine that the way I want to correct it is like I will do this of like window get body, it's get body. So I'm just putting it in the window object, and now when I come back to here, I look at the console, and I start receiving messages because small division. Okay, now, so I can just get, for instance, here I have like a final. So this is a block hash, right? So I can just copy it and do get body of this block hash, and then console log it. Console log, right? And when I do this, now it's complaining because like this is not implemented, right? But the idea is that this should return a promise that then will give me the body response, which is just like the array with all of the transactions in it. And you don't need to decode the transactions or anything, just like give me the body. Now, if you want to do this programmatically, so you don't have to copy and paste, then what you can do here is come here, and when you receive the finalized event, then from here you can just do like get body of the finalized hash, block hash, just so that you can you try it, right? Like if this is if the event is finalized, then get this body and you can await it, or then console log or whatever. The only thing to keep in mind though is that even though here we are only requesting for one body, this function can potentially be called for multiple bodies, like multiple requested ones, right? I want to get the body of these 3 block hashes, so I can call this function 3 times, and it should give me the correct result. Yeah, you could do it like this, where it's like, okay, I'm going to see the messages, but you could also theoretically use the JSON-RPC spec, which someone shared the link, which thank you for that, really. Because in here you have the JSON-RPC spec, and then here you can see everything that needs to be sent, and the follow. This is everything that we have seen. But for the time being, I'll just like copy and paste stuff here. So when I send a follow event with ID1, then I get a response with a result. So here's the subscription ID. And, so something we need to do first is like, well, I need to correlate this idea, right? Like I have sent the follow, so to get the actual follow subscription back, I need to correlate by this ID. So what I can do here is on this follow, I'm gonna put like let follow ID. is going to be string number or no. And now here, when I want to send a follow, I say like follow ID is this ID, and this is what I send to the server. And then here, back here, when I receive a message, if parse message dot ID is the follow ID, then I know that I'm in this message over here. Yeah. And now this message has ID, the follow ID that I have sent, and as the result has the subscription. So because I need the subscription outside, I'm just going to put it here. So let follow subscription, which is going to be a string or no to make it better. And I just like store it outside. So follow subscription, it's the parse message dot result. Nice. So now we have the follow subscription, and this follow subscription we can put it in here. Yeah. Now, okay, we need to get the body of this block hash, and now we have a follow subscription, which is on this variable. And what we will need to do is return a promise. Okay, so return new promise. And this is a bit maybe a sort of like advanced JavaScript, right? Like when you work with asynchronous and promises and everything, you usually just consume them, right? Like you have a promise, you can await it, and you get the value back. But if you want to create a new promise from scratch, because you are creating a new asynchronous operation, the way that you can do it is with a new promise. And then what you get back here is like a callback where you need to call resolve whenever this promise resolves. So like essentially when the operation is complete. Yeah. So first of all, here we have to do connection.send JSON stringify of JSON-RPC 2.0, and then the ID, I'm just going to increment ID by now. And then I need to look here because I don't have an example yet, but then I can come here on chain head v1 body. This is the request I can call, and it takes two parameters, follow subscription and hash. So copying chain head body. So this is method chain head body and params, I think it's called. I have it down here. Yeah, you see like it's method, the method you want to call, and params is an array of each one of the parameters. So we had the follow subscription and then the hash. So follow subscription, which is the variable that we stored outside, and the block hash. Okay. So here now this get body, all it will do is just like send a chain head v1 body with that. And here we could do something which is like, well, if the follow subscription, like if this is just defensive programming, if the follow subscription is null, then throw a new error of like follow not ready yet. And that's fine. And now just to give it a try, what we can do is this part over here. So if the event is finalized, just so that we can try without having to copy and paste everything, we can do that. So if we need to look for a follow event, and if the event is finalized, I'm going to see what it's sending me for a finalized event. Or initialized. I can do initialized maybe. This way, you know, I don't have to wait for a finalized event. Initialized. Then I have finalized block hashes, and I'm just going to take the first one. So then here I'm going to parse message params result finalized block hashes 0, because this is an array, remember? And then when I get here back the body that I will not get just yet because I have not implemented it, I will reset this. So in theory now, what should happen is that when I receive the initialized event, I should send Okay, something did not work because I have received the initialized event, and I haven't sent any get body thingamagic. So what happened here? Parse method. Yeah, but it should be fine, right? So, like every time that you send a message, you need to send an ID, and this ID needs to be unique. So before I send a follow, I increment the ID, and I just pass down this thing. And when I send the body, I also increment the ID because this way I'm not reusing it. What's because I'm waiting for finalized, not for initialized. That's the problem. Oh. So here I put like when it's a finalized event, I want when it's an initialized event. Let's see, this should work now, please. So in theory, when I receive the initialized, yeah. So when I receive the initialized event, you can see that I sent another request, which is change head v1 body, with two parameters, which is the subscription ID and then the block hash. And this is the part that I have not yet done, but then now the server like replies me with this ID. So I passed ID2, now ID2. The response is operation started, and the operation ID is this one. And actually, at some point, so then there will be like operation storage done. New block, test block change, new block. Maybe I can like operation. Oh, this is annoying. At one of these points, like a small dot will have, yeah, here it is. So in here, a small dot has already received the body of that specific block, and then it tells me operation body done, and here's operation. But I have not implemented yet the way of like resolving the promise, right? So let's work on that. Let me collapse the other messages that are not relevant, because otherwise I will. There's like a lot of follow events and stuff. So, okay, now first we need to parse this one. And the way that we have to correlate is by this ID, right? So we have sent an operation body request with this specific ID, and now we have to get the response. And again, like we are sending the messages on the function below, and we are receiving them here. So we need some sort of like data structure or state that will allow us to do that. So this is sort of like another assumption that I'm doing here, that you can see that there's only one follow subscription, right? Because here I have a provider, and then I'm only sending follow just once. I don't want to make this extremely more hard by having like multiple follow subscriptions, because maybe that's a bit too much. So this is why it's just like have one follow subscription, and that's all I need. Yeah. But now I need a way of dealing with multiple bodies, because this is something that I have asked, that you can request for multiple bodies at once. So how do we do that? Well, in here it's a bit the same thing. So this ID, I will need to get it from outside. So what I can do here is like, okay, this operation ID is what I'm going to send here, operation ID. And now I need to correlate that this operation ID is related to this promise over here. Can you see that? So here we have a problem, right? Like it's always the same thing. It's like this resolve function here, we can call it to resolve this promise over here, which will return the result. But this is only on, like this function is only in this scope. So we have to bring it out, essentially. We have to let this provider over here call that function whenever it's done, whenever it has received the result, right? So, and not only that, but we need sort of correlate that this operation ID is for this specific result function that we're receiving. So if someone calls the get body twice, we will create two promises, and each promise will have their own result, and each promise will have their own ID. And now we need to correlate those two. So is there a data structure that we can use for that? Yeah. Well, you could use an array and the ID is the index. But this would be one option if you have like if your IDs are numeric, right? Maybe you could run into a problem because as your application keeps working, then you're dealing with IDs which is like 1,000. So you need to have an array of like 1,000 elements, which is not great. So there's another one which is very similar, which is a map. Yeah. So if I have operation ID to resolve, I can create a new map of where the key is a number because I'm dealing with numerical values, and the resolve function is going to be like the result. So, right, this is essentially. Oh, sorry, result. String. So now I'm creating a map of each one of the operation IDs to the function that has to be called when that's solved. And this function is actually this promise over here. I can type it. I can give it a type so that everything is typed and nice. And now here I can say operation ID to resolve. Oh, this is not an operation. Like if I call this operation ID, it's going to, this is not a good name because we have another concept of an operation ID, which is like what's coming next. This is actually the request ID, yes? This is like the JSON-RPC request ID. It's not the operation ID. I'm sorry about that. So this is request ID to resolve. And we can set this to the request ID resolve. So now I think that in this part we're done. We don't have to do anything else now, right? Because, okay, we have received the follow subscription. We use it to send it. And now it will be the responsibility of whoever is receiving messages to give me the result once this is done. Yeah. So now that we have here, like I can even like collapse this thing. I don't need this anymore. And now that we're here, first we need to, because I have saved anyway. First we need to parse this thing, right? Because when we submit a chain head body operation request, we get back not the result directly, we get back an operation ID. So we need to see this. So what we can do here is, yeah. So if maybe I can like get the resolve function from here. So const resolve function is request ID to resolve get, and I will try to get the parsed message ID. So from the message, I'm getting the ID, and I'm using this map to get the value of that. Yes. And now, if this thing exists, because maybe it's a different ID that we don't even have, then we know that we are in this case. So what do we do now? Because like we have a result function, which is this thing that we can use to when we have the result. But what we have now is an operation ID, right? We don't have the result yet. So we cannot resolve it yet. But we need now to correlate because like, okay, so this operation ID is that the body is now getting fetched, right? And when the body is fetched and we get back a result of like, hey, this operation ID is now complete and you have here the result and so on, now we will have the result. So we have, again, to correlate this operation ID, when it gets resolved, we'll have to call that promise. That's a question there. Mike?
I'm not like exactly able to wrap my head around why do we need to like keep track of the promise as well, we can maybe simply like send or request the message and then wait for the logs to get that specific ID, and then maybe like get whatever like we want, the operation ID directly from the ID as well.
So, but I'm not really sure how do you correlate then what you have received with what call you have, right? How do you do that?
Okay. So ID won't be enough, you're saying?
What? Sorry.
So the ID that we are like passing to make the call, that won't be enough to follow the response.
Well, the only thing is that you have two levels, right? This is why it's a bit complicated, because so we have one level of IDs, which is the request ID, yeah? Like the JSON-RPC request ID itself. And this gives you back a message that has an operation ID. And then, with this operation ID, that after a while, then you will get the body response with that operation ID, but you will not get the original request ID. Like, this is completely
Okay.
gone. So this is only used once, right? You make a request, you get back just one response, which is just like, okay, this is the operation ID. And after a while, what you get is a notification from you get an event. And now the way that you have to match this thing is because that event has the operation ID that you received the initial user response.
Okay, so the response like won't be containing the request ID that we requested it with.
Yeah.
Okay.
I'll change my console log provider so that it doesn't parse the message anymore, because now, or maybe I can do, no. Just log me the message and that's all. Because otherwise I cannot find, like, when it's like, oh, I want to find this specific message, I have to expand them all, and it's a bit annoying. Yeah, so actually, like, this is the body. This is why it's like massive. But you see this thing, right? So we send a request ID 1 of follow, and we get back the response for this ID, the follow subscription. Yes. And now we receive a notification, which is a follow event, of this specific subscription that we have now, which this is now an ID. It's like a random string of that we can use with all of the initialized and everything. So with this, we send now a request body. It's a request, so we send ID 2. And what we get back is, for this specific request, the operation ID of the body is this one. And now if I find this thing, at some point, I receive a follow event of that specific follow subscription of operation body done of this operation ID. But now, this doesn't bring back the request ID that I have originally used, right? Like, because this is a notification, this is an event. It doesn't have that. So what it's using is like the operation ID that we have here. So this is why we have like these nested levels of like IDs and everything, which complicates things substantially. Yeah. So what I was here is like, okay, now we have like a request ID to the resolve, but what we have received is the operation ID. We cannot just resolve the promise yet. So if you want to correlate, you can, again, use another map to say like, well, now this operation ID is we'll need to resolve this thing. So I'm just gonna create a new map of operation ID to resolve. And here first I will delete this from our request ID to resolve, because I don't need that anymore. So request ID to resolve, delete parse message.id, because I have already received this response, and I will never receive anything else, so I can just remove it. But now I need to add it to this one. So set parse message.id, the resolve function that like the same resolve function that we have received here, now we're just like moving it to the next stage, essentially. Like this is just like one example. Like this is how I would do it, just like in this quick dirty example. But someone like would create like another data structure of saying like, okay, I have an operation and I have like different states, and then I use a state machine to track on which state it is, and maybe it's a bit more resilient. Like if you want to build a full library or whatever, rather than having global variables. But the concept is the same, right? It's like I have something that I'm just moving to the next stage, and now I just need to, detect when I'm receiving one message that makes sense and just moving to the next stage and so on. So the next stage will be this one, where I receive a follow event with all of the stuff. So when I receive a follow event, I'm just going to copy this other thing. So, and the event is a operation body done. Then what I have is operation ID is this one, and the value is the actual result. Okay, so I can get the operation ID. It's in here, operation ID, and the value is the result. So now what I need to do, like follow, sorry, that's from copy paste. So now what I need to do is get operation ID to resolve, so that I can call the resolve function. Maybe no. Yeah, maybe I can change the name this to resolve function, right? A request ID to resolve function, an operation ID to resolve function. That's a bit more descriptive. Okay, so now I can get the resolve function, which is operation ID to resolve function, get operation ID. And here again, we can be like defensive programming and say like, well, if that doesn't exist, then I will not throw any error, because maybe, I don't know, who knows, like it's benign, right? Like if it's sending me a message that I just don't know what it is, like, well, this is up for thing, but then I'll just like warn unknown operation ID, operation ID, operation ID. And here, now I can do, I have the value, I have the resolve function, so I can just do resolve function of value. And oh, yeah, of course. And then I rather, yeah, because like if I don't have, otherwise this would break. Nice. So now in theory, when I do this, now this should work. Unknown operation ID. Well, it didn't work. Let's see what went wrong here. Maybe this didn't work. Request ID if parse message ID. Now we are deep into a debugging session. But because what I saw here is that unknown operation ID, but it's giving me this thing, so it means that it has read the operation ID correctly from this message, but it was not added to our thing. So what could be doing wrong is probably here. Parse message ID. That's interesting. Else. So if we have an ID, I'll just log this and also the request ID to that. So this is expected because like this is the initial one, and it's like, well, I have received the one, but I have not seen it. And now when I send the body request, okay, that was funny because here I there was like a stop event or something. That's strange. So request body. So maybe it did went through. Then what's the problem? If anyone just sees it clearly, just please tell me. But at this moment, I'm a bit. Oh! Of course. Now I've seen it. What have I done here? So I took it out from the request ID to result function, right? I took it out from there, but then I added it, and the ID I put like the ID of the request, right? I need to put the operation ID, of course, right? You can like you can see my bug, right? Like, so I have like a one map which is request ID to resolve, and then I have another one which is operation ID to resolve. But what I put here is the request ID. And this is also because this is like actually a string. So I need to get the operation ID, which is just the ID. Okay, I have result dot operation ID. Operation ID. So if I have not done anything wrong, then this should be working. Yay! I got it. Okay. And it's like this the console message is the one that we're looking for. And this will actually work if I do multiple requests at once. So if I do that instead of like on initialized, I do it on finalized. And let's see, because I don't know by heart, finalized. So event finalized, and there's these finalized block hashes. There are multiple ones, so I can do const results is await promise all of let me see again the shape because it's a event finalized block hashes. Yeah, so finalized block hash this one. So for every single finalized block hash, I need to make this async first of all. That's fine. So for every single of the finalized block hashes that I'm getting from a finalized event, I'm gonna do get body of that specific hash. Yeah, right. Because this is not typed. This is what someone here mentioned, that these are not typed, but this is because it's JSON, and when you do JSON parse, it just doesn't really work. So all body is its results. So I hope you're also familiar with this promise all, right? So this is like getting each one of the hashes and mapping this array to a new array that does get body hash. So this returns a promise. The result of this is an array of promises. And now you do promise all so that you get just one single promise with all of that result with the array of that. So now if I filter all bodies, so you can see here, I'm receiving each one, and hopefully if we have like a finalized event that has more than one hash, it should actually resolve with the two of them. But I'm not receiving any finalized event with more than one hash. Well, this is because it's a live chain. Anyway, it should work like believe me.
Going back to the developer dev tool,
Mhm.
it said 3, then 2. Is that because the items that are getting added are like suddenly removed from finalized, or why is it going from array 3 to array 2 on all bodies?
Oh, like so you can see that this is like actually an array of an array, right? The only thing is it's an array of only one element, and this element is an array of 3 elements. So you can see that this is an array of only one body, essentially. and this one has 3. So it means that this body had 3 transactions in it. Yeah.
Oh, cool.
If we go to DevTools, model was quick enough. Yeah. So if we go to anyone, so wow, this one has like a lot of transactions actually. But children, usually you can see that the blocks are mostly empty. So this one only has 3 transactions, and this one only has 2. But at least on Polkadot, you will always have these 2 transactions. You will have timestamp set, and then the parent parent enter, and this is for the parachains verification of that. Then in theory here, yeah, you see like that block that had like a lot of transactions, it's this one. So you can see all the transactions here. The only problem here is that Grandpa now is working really great. So now we're getting finality very often. If actually maybe, I don't know. I was going to say like maybe I can like shut off my network, but then this will go out. And I don't think I can say, because I think that this offline is for new requests. I don't think it will matter for. But what I'm trying to, oh, maybe it does work. What I'm trying to do is like, okay, I'm disconnecting for a few seconds so that, you know, there are some blocks coming through. Now maybe, no. It again finalized one by one, and I don't know. Anyway. What else I want to mention is this thing, right? Like in here, we made the assumption that there's only one follow subscription. In this case, it's fine. It's this example. But if you are building a library, then you have to take into consideration that you have actually a follow subscription. So you also need to do like this correlation also for the follow subscription. Even inside here, right? Inside here, the message that I'm receiving here is all of the messages that are going through the same WebSocket connection. So in here, when I do operation body done, this operation body done also has the follow subscription. So in theory here, to be absolutely correct, I should do like if parse message.params dot follow subscription is my follow subscription to make sure that, you know, I'm just listening to my own stuff, right? But again, like in here, we're just like, yeah, it's a singleton. We only have one subscription, and that's all done.
What you can do is like have an internal state, like maybe a class or an internal state that's just holding like those IDs, right? And then you have a switch case where now you're just like switching through events, and then each event you're parsing now through the data on the event and then updating your state per. So I'm just imagining, like my question earlier was like, why isn't there a wrapper library? And I'm thinking about how that would be implemented.
Yeah.
And yeah, basically you would just kind of have
yeah, absolutely.
internally tracking events and then internally updating state within. Oh, well, there you go. Okay.
Yeah. I'll cover this one later, but absolutely, like in here, I'm doing everything like a dog, right? Like this is absolutely, it's very hacky, right? It's like, oh, I have this message, so I'm just if matching each one of the messages, and you know, this is only for one specific operation, which is body. Now imagine for all of the operations, but also you have you know, waiting for continue, and also if we take a look at the follow event, well, I was actually here. So we have like the easy events, but then we have operation body done, operation call done, and so on, operation storage items. But we have, for instance, operation inaccessible. So operation inaccessible means that at this point, this operation cannot be dealt with. Please come back later, right? And then, you know, this is something else that you would have to deal with it. Or operation error is like, well, this body for some reason I cannot read it. So there's an error that. So yeah, this is absolutely not the way of like building your own production ready stuff. But you know, for the purpose of this demo, then it's just fine. There was from what I have seen, there was also another solution that someone did, which I think it would be okay as well for this kind of thing, which is like instead of like taking this resolve function out from here, it was setting up a state, and then from here, it was essentially polling. So it was doing set interval of like, I don't know, every 100 milliseconds. I'm going to check if my state, so like it had like a structure up there, which is like if the bodies that I have loaded, of this specific ID is done, then resolve this thing, right? This is maybe another way of doing it. The only problem with that is that this thing is getting called every 100 milliseconds, which is like, personally, I prefer, and actually I think, well, yeah, of course, like our library does this. Is like, well, this result function, I can just move it out so that, you know, I don't have to essentially poll for it, right? Whenever it's ready, this function gets called, the promise gets resolved, and everything is perfect. I'll commit this thing. That's good. And now maybe what I can show is the library that we have that does this thing. Yeah. So it's not part of the top level library. When you do Polkadot API, install Polkadot API, internally, it's referencing this library, but it's not exported. So if you want to use it, you have to install it yourself, which is install at Polkadot API /substrate client. So now I can import it. Import, and it has the same name as the top level client. So this might be a bit, but you know, essentially like it's either you're working with the top level client, or I think it is right. Create client. Or if you want to work with more low level stuff and create, I don't know, like at this point, I don't think we have any use case, any valid use case of like someone who would, like maybe if someone wants to create an alternative version of Papi, then they can use this so that, you know, at least you have all of these shenanigans solved. So the provider, I'm just keeping it, but now all of this, I can just remove it because I'm doing all of this. And I have a client, it's a create client. And again, what this function takes is just like a JSON-RPC provider. It's everything it needs. But now it gives you a substrate client. By the way, why is it called substrate? You know that? So this is a bit of like the history of Polkadot. So before Polkadot was like 3 separate repos. There was substrate, there was frame, and there was cumulus. And at some point they decided like, oh, no, that's too complicated. So we're just merging everything into just one single repo called Polkadot SDK. And they rebranded everything to just Polkadot. So initially there was like this substrate-based chains that was using substrate as their node. Now that's not anymore the case. Now everything is Polkadot, basically. So now that we have this client does nothing by itself, like it doesn't start any connection or whatever. You have to do client dot chain head. So like this client does all of the JSON-RPC stuff, right? So this is why you have archive, chain head, transaction. So each one of these is their own group of functions. So I have to do the chain head. And when I do this, now I'm calling chain head follow. So now I can pass like with runtime true or false. I'm going to pass through. And then this is a very unopinionated library. So it doesn't use observables or anything. It's just so that, you know, anyone can use it and they can use whatever observable library or like concurrency stuff they want to use. But in here you receive the follow events, the console log events. And if there was an error, then you receive it as a separate message. But that's not really. Oh, I guess I actually need to pass errors. Okay. Oh, yeah. It actually makes sense. Like, this is very important. Yeah. Sorry. So it's one of, like, the events that we're receiving in here are only the events that the node is sending to us, right? So it's just sending like initialized, new block, best block. All of the other events of like operation storage done, operation storage call done, or whatever, or operation inaccessible, all of these are not going through here. They are being correlated elsewhere, right? So because that's the whole point of this library, is that I don't need to correlate. It's doing it for me, yeah? And now this error, for instance, is when we receive a stop event. So a stop event is theoretically an error because now this connection is done. So this is what we receive through here. And I'll do an error here. And so now the question is, what if we want to send a body and get it correlated? So what chainhead returns is chainhead is an object that has every operation in them. So what I'm going to do here, and this is fully typed, by the way, so you can see if the event.type is finalized, we're going to do the same exercise here. So if the event type is finalized, then you can see that now TypeScript has, find out like the actual type of the object. So now you have like all of this here, and so for every finalized block hash, I'm going to map this. So I have the hash into chainhead.body. And chainhead.body, what does it take? It takes a hash and returns a promise of string array, which is what we have done here. So nice. And now what I can do here is make this asynchronous, and now on bodies is await promise all of this. Now console log bodies. So with this, we have done the same thing now that we have done in the exercise, but using this library that does it for you. You don't need to worry about it. Oh, because I'm console logging the messages as well. So these are the events. So I received initialized event, then new block, best block change, and so on. Now, when we get the finalized, at some point here we have the body response. So now here we have the body. Yeah. Another body with 3, and so on. Oh, operation inaccessible. That's interesting. So at some point we requested for a body, and actually the node told us like, I cannot get this body for you. So now this promise over here, one of these promises that was in here has now rejected with, hey, this body that you have asked has thrown an operation inaccessible. If you want, you can retry again. It does, again, like this library is completely not opinionated at all. All it does is just like correlates messages and puts types on them. So now the logic of how you want to do the subscription and how do you want to deal with errors and how do you want to, use the concurrency, like if you want observables and all of that, then it's up to you. Yeah, but the problem of correlating and also like the TypeScript, which is like extremely useful, then you have everything in here. So continuing moving forward, then it's more or less the same. So when you want to do a runtime call, the only difference with the body is that now you have to pass in parameters, right? So you do chainhead v1 call of that follow subscription for this specific block. And now you pass in the rest of the parameters. So the first one is the name of the runtime API. And the next one is the scale encoded version of the parameters of this runtime API. And same thing. So first, like it's not here because we don't have enough space. But what you get back from here is operation call started with an operation ID, and then you get operation call done with that, and the scale encoded version of the actual values. So here I had like another hands-on, but I think it's more the same. So I'm gonna skip it. So like this, it was essentially like instead of getting the body, we get the metadata. But the metadata is the same thing, but uses like passing, and I think that's any difference. Well, The only difference is that now you would have to scale encode this thing, right? So when you do a metadata, you need, well, this exercise was to use metadata at version, so you would have to pass in the version and then decode the metadata. We could do it, but I don't know. Like it's like we have. I think that we have already covered both things of like encoding and decoding types, and correlating messages. So, or maybe what we can do is just like show how this can be done with a substrate client. So this way it's not as like dirty up and down. I think this could be interesting. So here we have client chain head, and whenever we have finalized, oh, this is going to be, no, I'm going to do like when it's initialized, because the metadata is like massive. Otherwise, I will get like a lot of requests and so on. So on initialized, I will just get one of the block hashes, which is going to be this one. And what I need to do now is ask for the metadata. So I'm going to grab the chain head object that I have from substrate client, and I have here a call, which again, call is for runtime APIs. Sorry, what am I even doing here? So, and as the hash, I pass in one of the finalized block hashes. Now I need a function name. So at the moment, I will just put function name here. And then I need a call parameters, which is also a string, which is like the hex encoded, so I'll do 0x at the moment. And now we have to fill this in. So the function name, we can just go on the DevTools, random calls, metadata at version. And now here we can see, well, first the name is metadata underscore metadata at version. So we can just add this in. Metadata at version. And now this thing has to be scale encoded. So here you could say like, I can just pass 14 here, but that's not true. Like, remember, the substrate client, all it does is just like the JSON-RPC correlation and all of that. Now, if you need to encode and decode stuff, you need to know how to do that, right? So in the case of metadata, this is interesting because it's like the metadata it's telling us that there's a runtime API called metadata version that has one parameter, which is version, which is a U32, right? So you would say like, well, I need the metadata to know this thing, right? That I have this runtime API that I have to call. But this is like a special one. So this is why they try to make it as stable as possible. And they do not break it at all, because now it's an assumption that you can make. Okay, you don't need to get the metadata to see this type. You have to know that there's a method that exists that's called metadata version that takes only one parameter, which is a U32. Yes. So now what we can do here is encode a U32 of 14. That's interesting. I don't think. So for this, I have another library of Puppy, which we have to install. npm Polkadot API, and it's substrate bindings. So we have substrate client, which is like to connect with substrate-based chains and do whatever. Substrate bindings has the codecs and the types that substrate chains usually have. So now I can. So this way I don't have to manually encode and decode the U32 and can't be bothered with that. Well, I could actually do it, but no. Substrate bindings, substrate bindings, and here you can see that here there's like many different types. We have account ID, binary, bit sequence, all of the hashing functions that substrate chain have. We also have the codec types, so like the codec type and so on. But we also have the codecs itself. You see SS58 string is also here. But here you can see all of the codecs. So we have compact, we have Boolean, we have void, which is another one, all of the integers and so on. So I just need U32. And here I would do U32 encode 15. I want the metadata version 15. Now, what the codec returns is a binary. So we need to turn this into a hex string. So we have another method which is toHex on polkadot that takes any binary and turns it into a hex string. So now that we have done this, we can receive the result. So the result is await this. And now the result of a call is the hex encoded value of whatever that has returned. Right? So if I come here and I want the metadata version 14, 15, what I get back as a result is just like the, all of that. So in here, what I can do now is that we also have a function of decode any metadata on substrate bindings that you just pass in the result, and you get like the metadata back. Cons metadata. Oh, wait. Oh, no. So this is it. Like it's pretty clean, right? So again, like this deck any metadata, you can see, well, what it returns is actually the whole data structure of the metadata. So the metadata at the beginning has a magic number that is just a constant that all the metadata has, that it's just used to say like, oh, this is a metadata. Like if you ever open a PNG image or a JPEG image in a text editor, you will see that it always starts with JPEG or PNG, and like this is more or less the same concept. I think in ASCII it has something, Carlo. So the magic number of the metadata, I think that in hex is something, it's meta. Yeah. So if it's meta in ASCII, is this magic number essentially, but that's all there is. And then the metadata itself is like this enum of which version it is, right? So we know that it's going to be version 15, but what we get back from the metadata is, it's the whole actual object. So deck any metadata is just this massive codec that just decodes any one of them. So if I come back to here, my example, and I don't put it in pause, this should work. So again, like it's doing all of the correlation behind the scenes and everything, but when it connects, oh, come on. There it is. So we have done the chain head call with the, for this specific time. And then we have metadata version and the scale encoded 15, sorry. And now we have received the response back, and it has been decoded into this metadata version 15, and here's all of the metadata. Fetch metadata. I think like this playground that I have here is because the initial idea was to have not the correlation exercise, but have this as like that puts everything together. But it was way too much, so this is why I decided that we should do something a bit smaller. Okay, so now let's talk about storage, because there's an operation that's missing with the chain storage, which sounds like it should be easier, right? It's like it's doing less than a runtime call, but it's actually more complex because you need to understand the structure of the storage on chain to actually use it. So we know that the chain has this state transition function, and the state is something that just keeps mutating. But we need to understand how this state is structured in order to query it. So from a high-level perspective, it's just a key value store, right? There's a bunch of keys. So the balance of Alice has this value. And the balance of Bob has 72 dots. And also for other palettes. So you can have like the assets. And you can query for, well, the assets of Alice that are USDC are these ones. And the votes that Bob has done on medium spender are those ones, right? So it's all like key values. Like I have this key, I have this value. I'm hearing myself. It's not good. Okay. So this is the high-level view. What is the low-level view? How is it actually stored? Well, internally, it's still a key value store. But instead of like being just like, one single map, this would be like a massive map. It's not performant, and most importantly, you cannot build proofs with a map. It's a key value store, but it's Merkleized, right? And you have taken a look at Merkleized in fundamentals, Merkleized data stores, but I think it's good to do a bit of a recap here. So if you remember, a Merkle tree, it's a tree of where like each one of the keys brings you to one of the nodes, right? And then everything is hashed, and everything essentially is tied together with hashes. So the purpose of this tree, if you remember, is because then if you want to get one value of the key, one specific value, and make sure that they are not lying to you, as long as you have the root hash, you don't need to receive all of the values to check that the hash is valid, right? You can only receive the value that you want. So let's say that you want Alice. And now you can get the Merkle proof of each one of the neighbors. So you're essentially cutting down all of those values out and just getting the proofs, which is very nice. Yeah. So now what we have under the hood is actually still a key value store, but it's a key value of each one of the pieces of that tree into their node value, right? So here we have like a key, which is a hash of a value to its own value. And we have another key, which is just a hash to its own value. And now we have another key, which is like another node with another hash, that now the value of that is like one of the other rows, right? So we have Alice has this hash, which then we could go and find out the value, and Bob has this hash, which has the other one, right? And so on, so on, so on. So this way, why is it structured this way? Because if you ask for the value of Alice, but also give me the proof, right? Now we can just like follow this structure. So we come from the root, and it's like, okay, I want to see the balance of Alice. So assets and votes, I already have their hash here, and I don't need to dig down on them, right? I keep those ones. But now when I go to the balance, I need to fetch the balance of Alice. So I need to see like, okay, now this hash, where does it take me? So it's 7F41, it's taking me here. So now I need to see like, okay, Alice, I will fetch it, but Bob has this hash. I don't need to look for anything else. I know the hash of Bob, right? And then Alice, I can follow here and bring it back. So this way, when I'm asked for give me the value of Alice, I can give you the value of Alice, but also the storage proof without having to, read the whole database. Yeah. The thing is that there's a bit more, right? To that. So whenever we see this, this thing has a problem. Like it's one of these things is part of the key, right? We have balance of Alice. So this is susceptible what it's called a key length attack, I think. Yeah. Which essentially it's extremely important to get this kind of tree balance, what it's called balanced, right? So a balanced tree means that it's a tree that, every single leaf has more or less the same amount of children. You don't have like the root and then like an extremely long chain on one of the branches and then a really small one on the other one. So if as an attacker, you can create one of those entries in here that you're putting a lot of nodes on that part of the branch, now your tree is not balanced. So what could happen in this case is that you could essentially take down the network, because if you make something really big on one of the branches, then when you ask for proof of the branch, the proofs are massive, and the nodes have to work like a lot harder to prove everything. So essentially bringing the node down, right?
Yeah, just to connect it with what we said yesterday, do you remember that we had these hashers, that we had multiple hashers, and some of them were concat and some of them were just the hash? Here is when we need just the hash, right? In case the key can be, so the length of the key can be chosen by the user, more or less, it's when it's interesting to use the hasher that it's opaque, essentially, that it does not include the whole key. Make sense with what we said yesterday?
I don't fully agree with that.
You don't?
No.
Like if you can, so the
So-
thing is, what if you can create a lot of nodes?
No, because like the way it works, like it does it. Sorry, like I'll explain this. So the thing is that these things, they don't go like nibble by nibble, right? At some point, like if there's only from one node to the other one, everything is just like, there's like a yeah, exactly. It's a partial key, right? So it's not that the key is extremely long so that it has to go like a lot of steps below, because if there's like one of the keys, I don't know how to show this. Maybe.
Yeah, exactly. Is that if you can create multiple keys very long with only the last nibble different, or only a few nibbles different in the middle.
Yes. I think I have to stop sharing because then people at home can see it better. So we have the root node, and then we have like a lot of branches and so on. Yeah. What this attack does, like, well, first of all, like if we have, for instance, imagine that we only have one account, okay, on the whole system. So we have system account. I'll do it a bit bigger. We have system account of Alice. Like theoretically, what would happen here is that, okay, we have the root node, and then this branch, the key is this thing. It's the whole, like, that's the whole key, right? And here we have just the balance of Alice. Yeah? Now, if later Bob comes and creates a new key, which is just a system account of Bob, now what will happen is that this key will actually become a node and then get split in two. So we will have system account, which is going to be this branch, and then we have two other branches here, one for Bob and another for Alice. Yeah. So what I meant is that like the length of the key, it has a very small impact. Like it does have an impact. Like, you know, if it's like unbounded, then of course like that's problematic. But the attack I was talking about was that if you have the users be able to choose at which branch they want to store their data, right? You could create something which is just like, okay, I'm just going to create Bob 0000000, and now I'm just going to create Bob 0001, and then Bob 0002, and Bob 003. And what you do with that is that you're putting a lot of nodes on the same branch. So this branch is going to grow, and it's going to grow, and it's going to grow, right? And now when you do operations that touch this branch, you're creating massive proofs. That's it. Yeah. So what is the solution to that? It's related to what he said, right? We use hashing algorithms. So if instead of doing system account, we make the hash of, well, system account, maybe we don't need that. But if we, instead of using this as a key, we do the hash of Bob, hash. Now we are essentially randomizing the key that the user can put. So they cannot longer do this attack. Yeah. Now on that slide, so I'm just going to continue what that slide explains, is that for us that developers, like this is annoying, right? We have a storage that now the keys are all hashed. So at some point, if we say like, okay, give me all of the system accounts, it will say like, okay, the account that has a name of this hash has this value. And it's like, but who is that? We don't know, right? So this is why we have the hash concat, right? So we have like Blake to concat, or Blake to concat. So what this is just like Blake2, the hash of Blake2, and then concat the original value. So we have a Blake2 and then the name. So this way we have like the best of both worlds, right? Okay, the key is larger, but that's not a problem because like we're not making the tree larger. We are still randomizing the keys, so we cannot get attacked, and we can still decode back the result. Yeah. Now it's true that there are some storage entries which is like an XCM message, right? And an XCM message can be like extremely long. So if you want, to say like, okay, I don't want like extremely long keys, then you just use a hasher that's not a concat, and now your hash is small. But now you have the problem that you will not be able to decode back the original message. But I mean, that's a problem for another day, I guess. So yeah, essentially this is what I explained, right? So if the end solution is to do this concat. So we make the hash of balances, and then we put, okay, this is balances, and then we make hash of Bob, and we put the string Bob in it, so that we can read it back essentially. Okay. So well, this is just a bit of more recap. So like the key concepts of this is that you have a key, which in this case is one of like the union of that, so balance Alice. Then we can have a value, which is that. We can have a hash. A hash is just like the hash of the value. And the Merkle value is one of these intermediary points, essentially. So now, with this in mind, there are some limitations. Like there are trade-offs with this sort of database, right? So there's stuff that you can do and you cannot do. So what can you do? Well, you can access the value, of course. Now, there's another great advantage is that you can, like, given two different states, you can quickly see what has changed, right? If you had like just two maps of the key to value, it will be like really hard to know what has changed because you will have to compare one by one. But in here, you have like the Merkleized structure. So you can just like compare each one of the nodes to the new one. And if that is equal, then you know that everything below that node is the same as before, right? So it's really simple to see from one block to the other what has been updated. Another thing that you can do is, okay, give me the values that are under this key. So you just give a partial key, and everything that's under the node, you can get all of the values, and also like the storage proofs, which like this is the main point, right? Like the other ones come for free. Like the one that this was done for was actually to get the storage proofs to have like a trustless way of getting that. But now there are some trade-offs. One is you cannot query values. What I mean by this is that, with SQL, you can do, oh, give me the values that, where give me all of the counts that have a balance greater than 100 dot. You cannot do this with this, right? You have to get all of the accounts and read through all the accounts and, filter them. Or do the reverse search, right? Like, give me everyone who has voted this specific outcome. You cannot get like the previous one. Anyway, so now with that out of the way, we have storage queries. So this is all what it takes to make a storage request on JSON-RPC. This is a JSON-RPC request for a storage. So there's follow subscription. We already know that. The block hash, okay? And now you have an items array where you need to say like what do you want to access. So this is like the only one that the only JSON-RPC operation that you can do multiple requests at once. Just like support that. And then each one of these requests, you have to say what type of request you want to do, like what do you want from the chain and for which key. Yeah. So you can say, give me the value of that key, or give me the hash of the value of that key. Then we also have closest descendant Merkle value. Anyone can guess by name what that means? Closest descendant Merkle value. So this is like, remember, we have like the whole tree, the whole Merkle tree, right? You would use closest descendant Merkle value for only partial keys. So you ask for a partial key, and you ask, what is the closest descendant Merkle value of that partial key? And it will tell you, the closest descendant is this node. So it will give you everything, like the Merkle value of the node of that key that you have passed in. Why is this useful? Because with this, for instance, you can look for differences, right? If you want to know, were there any changes on the accounts palette, or on the referenda palette? Oh, yeah. Then you can ask, well, I'll get the partial key of the referenda palette, and I'll ask for the Merkle value, essentially, of that. So it will give you a Merkle value, and if that Merkle value is the same, you know that it has not changed. Yeah. And then we have descendant values, and this is more or less the same. This is meant for partial keys. So it's like, give me all of the values that are under this specific key. And the descendant hashes is the same thing for hashes. Now, lastly, we have a child trie, which usually you would just put null here, and it's a bit advanced. The thing is that we have, like, the state is all in a Merkle tree, but we have some parts of the storage which are not in the main Merkle tree, and this is called child tries. For instance, smart contracts. So smart contracts, they do not have their storage as part of the main tree because they thought that this would be not like anyone can spawn a contract, and each contract has their own instance and so on. So they decided to move the storage to what's called these child trees. So if you want to query the storage for one specific smart contract, you would use this parameter. Most of the time you don't. And actually, like, there's a runtime API, which I think is better to query the storage of a contract.
Yeah, I have one real question, so I'm not commenting anything. In the child try, how is it? So it has to make part of the regular try at some point, right? So with maybe only the root hash or something, or which is the security it can give? So does it share the same security with the regular storage? Is the root hash posted or something?
I think it does, but I would have to look it up. It's not part of, like, the main tree. It's like in a separate.
Okay, so maybe it's just a node. Honestly, it's a question. I don't know.
Yeah, so. But the thing is that you wouldn't find it on any of one of the palettes. It's not like the contracts palette has a place where it stores all of the trees. It's like in a separate. It's like a completely separate tree, but the state root hash does include that.
Okay.
Yeah. So if there's, well, we can continue. I can, like, if you have any question at any point, you can just raise your hand, and yeah, that's good. So yeah, like, as you can see, like, when you make a storage request, you can ask for multiple stuff, but the node might tell you, like, hey, like, I know that you requested for 10 items, but I'm just going to serve you 5 because I'm too busy. So when it starts operation and gives you the operation ID, it tells you the last 5 items have been discarded. So that's not bad. Like, it's not a bad thing. It's just that the node is telling you, like, hey, I'm quite busy right now. I cannot do all of the requests that you asked for. So I'm just discarding that. Usually these discarded items is 0, but you need to say that. And then when you receive back the response, you receive you can receive many operation storage items as the node keeps getting those values from. And then each one of these has an array of what it has found. So it will give you a key, and then depending on what you have asked, then the value of the hash or the closest descendant Merkle value. And at the end, it will tell you operation storage done, which means that I have sent you everything I need. And this is what I mentioned before, is like there's another event, which is operation waiting for continue. So imagine that you ask for all of the accounts. There are so many accounts, right? And so this is actually done for the dApp, right? Because like usually the server is like quite powerful, so it can send like a lot of messages and so on. Usually it's the dApp that has to decode these messages, that if it gets bombarded with like 1,000 like or 1,000,000 messages, then it can, you know, become unresponsive. So it's just like configuration based that, you know, after sending, I don't know, like 1,000 messages, it will send operation waiting for continue, so that the dApp now has to say like, okay, I have processed everything that I need, you can continue. And it will keep sending messages back. Okay, so you can say like operation waiting for continue, and then when you say like, yeah, I want more, then you can just say continue, right? And if you don't want, and if you for some reason it's like, oh, I have enough messages, then you can do a stop operation to say like, I'm not interested in this anymore. There could be a question here, which is like, is this pagination? Like, well, in a way, it does look like it's pagination, right? It's like I'm giving you 1,000 and now waiting for continue, and you can continue, but it's not meant. It's not really meant for that. So for Chainhead version 2, we are thinking, you know, because we are thinking of like opening the discussion already, and you know, usually pagination comes from the needs of the dApp, right? Like the dApp is like, okay, I want to get the accounts, but I want to get the accounts 10 by 10 because, you know, my dApp is just like showing like page by page and the user has to click through. So at the moment, there's no possible way of doing pagination with Chainhead v1. Maybe with Chainhead v2 is something that we can ask for and open the discussion if it's something that actually makes sense. But then we need to talk about how does this pagination work, right? Because it could be a bit complex. You know, I don't know. We have to see how that will work. But now, like, if you need to show all of the accounts, you have a problem. That's only it. Mhm.
I was just wondering, is there a way that you could search up people's, well, users, all the storage based off of a user's address, rather than having viewing it's based off of the specific storage information?
So, well, you can only query by partial keys, right? So you could theoretically, no, because it's hashed. So it's really hard to say like, okay, give me all of the accounts whose public key begins with that, because as it's hashed, it's all random. But you can, essentially, you could do some sort of pagination by saying like, okay, instead of like asking for all of the accounts, I'm going to ask the accounts whose hash begin with these 4 bytes. I don't know. And then you will get like a subset of them on every single one.
Then how do you explore, I think what you just said, the keys themselves? How do we identify which keys are relevant for us to be able to search for storage and search for balances or any other sort of asset?
Well, that's the thing, you cannot really query. Like it really depends on the storage structure. Let me see if I have, no. Because here I wanted to actually talk about this a bit, because for instance, if I go to the storage and it's like, okay, let's find, you know, on referenda, right? So I can do referenda, and it's like, how can I get like, you know, so in theory, like these referenda is like all of the referendums that are in Polkadot currently, and you would imagine that, you know, you have a specific referenda and you have the votes for that referenda, right? So let's see, like, if I can get the referendum info for, that's interesting. I can actually query all of them. Hopefully there are not too many and I can load them. Otherwise, I will have to look for one of these. Software. Okay, here I have many, but the thing is that these are all done. So when they are done, they are essentially sort of removed from chain. So this is why I want to get one that's actually alive. So this one is deciding. Okay, this is a good candidate. So 1722. Let's do this. 1722. Right. Okay. Here we can see like, oh, there's information here. Hopefully I got the list of votes. So I have the track, it's a spender. the proposal. So this is like the call data it's going to call. Enactment, who submitted, who decided, like, this is like who paid for the submission deposit, who paid for the decision deposit, and how much. And now some timing information of it's been deciding since this block. Oh, and look, here I have like the total amount of votes. That's nice. So in here I can see like, okay, this has, I don't know how many bazillion A's and how many bazillion A's, but where are the votes, the individual votes? Like if I come here and I take a look at here, I can see, you know, House DAO has voted with this amount and the Kusk has voted with this amount and so on. Like, where is this information? I don't see it here. So turns out that this is not here. I think that this is, maybe I'll open a new one. So I think that this is in conviction voting, voting for. And now here you can see that we have account ID. So it's like this specific account ID. So we can put here because I'm not active in, sadly. I should be active in, I should be more active in OpenGov. I'm just going to get OpenGov. And here you would say like, and what is this? Like it's a number, is it the referendum? No, it's not the referendum. This thing is actually the track. So it's on track 33, which is medium spender. So in here is where you can see the votes of this particular person, right? So Chaos DAO has voted on referendum 1,500. It has voted 3. So this is nay with conviction 3, because remember that the vote is like compressed and everything with this much balance, right? And so we can see here all of the votes for Chaos DAO on every referenda for the medium spender track, which is ID 33. But now if I want to, you know, it's like, okay, I have one referendum and I want to know who voted on this referendum. I just cannot do it, right? The only way I can do it is if I actually get all of the votes of everyone and aggregate them and I give them to you, right? And this is why we have like, essentially Subsquare is doing this. Like they have an indexer and they keep track of their state on their own database, right? And then they also offer an API, but this is not part of the chain. This is all of chain. So yeah, it's a bit. You have to work with this thing, right? It's like in here you could say like, well, instead of I don't need to pass in like the 33 here. I can say like, give me like every single vote of Chaos DAO. Okay, you have it. Like sure. After a while, it will load every single one of the tracks and it will give them to you, but you don't have any way of querying. Like the only way that you have of querying is if by pure chance, the structure of the storage has the structure that you actually need. Yeah, like in here I can ask for all of the votes of Chaos DAO, but I cannot ask for all of the votes of the medium spender track, right? Because you see there is a PAPI console here. If I say like, I don't want to pass this, but I want to pass this parameter, it doesn't let me. And why is that? It's because the storage key is given by conviction voting, voting for, and then it's a storage key. So it's like, it's everything is concatenated, right? So I have the count ID, and then I have the track number. But I cannot have the track number, which is like like, well, I'm doing it the opposite, right? But I cannot have the track number, which would be on the end side and the palette, and leave this gap empty. Like there's no way I can represent this. You see? So I can ask for a partial key of give me everything that's under the Chaos DAO account, all of the votes that are there. But I cannot do give me every vote that's in the medium spender track because there's no partial key for the medium spender track. Yeah. There's a partial key for medium spender track of one specific account, but not for all of the accounts.
Just dumb follow-up question. So if you disable both of those and press query anyways, does that go for every track and every address?
Yeah.
Okay, so
if you do this, like, it will probably just hang. It depends on the amounts of people of the accounts that are actively voting. But if there are too many, then this is going to take forever, and it will just not load. But theoretically, yes. Like for any other thing, like I don't know, like the other time we did proxies, right? So proxies, there are not so many. So I can ask for one specific proxy, but I can say like, no, just give me every single every proxy that's there, and after some time, it will load all of them, which there weren't too many.
Okay, so if you scroll up, so the entry is the key pathway for the Merkle tree, and then the palette helps, I don't know, stores it elsewhere. So
Yeah.
people are referring to the palette, then the entry, then the inputs, and then they press query. So that's, oh, yeah, cool. Yeah.
Yeah.
Okay,
So
that makes a lot more sense.
you can see like this encoded key is proxies. If I change the proxies here to announcements, you'll see that only the last part will change. Or maybe not. Maybe I'm wrong here, but so 18097 blah blah blah. 18097. But you see that here it ends with C85. I do announcements. It ends with another thing, right? So in this encoded key, we have proxy, then announcements, and then here we can select the account. So now the account is put over here, and first, the only thing is that I don't have an easy way of showing this. But if we take a look at this, with what? I don't know, I'll put this one, and then I'll put another one of this one. So what we have here is like a common part, which is up to here. So like up to 1B is the palette and the entry. And then we have the actual key. And this key first has the hash of the account that we selected. And at some point, it starts with the public address of that account. Right? So now we have the hash and then the account. This is what we mentioned before. Yeah, because it's 2x64, so this is the hasher, and then concat. So it has both of them.
There is a question in the chat that says if there is no set like hard limit on the amount of on the number of entries that the JSON-RPC can return.
No, the JSON-RPC doesn't define any limit. Like it's up for the node to decide. From my experience, small dot, if you make a very large request, it seems like it just hangs forever and it will never tell you. If you ask a full node, for large request, it works a bit better. And it just will tell you the results straight away. And this is for a reason that we will go through in just a minute. But hopefully this makes it clear of like what are essentially the limitations of the storage, right? It's like, well, the storage is very powerful, but the way that it's structured, it means that you cannot query it the way that you want, right? Like you have to stick to whatever the protocol track essentially has built for their pleasure. So yeah, I think this clears up. Any other question? No. We're back here. So this is what I was just now mentioning, that the live client has a hard time answering for big storage requests. So there's an RFC. So the RFC is the formal way of asking for protocol improvements. And we have this RFC here that was merged just 9 months ago, but it was created like 2 years ago. So it took a long time to merge, and this is by Pierre Krieger, also known as Tomaka, also known as the creator of Moldot. And what it's saying here is that currently, with the current protocol, there are like these 3 problems. They are described here. I'll actually paste here if you want like to later take a look. Well, on this question that we saw before, because yeah, this is when I saw when I have shown the substrate client, it's typed, right? So it has all of types, but before metadata v14, it has unknown because, yeah, before metadata v14 was quite useless, so we didn't spend time on giving those types. Anyway, so there's a bit of, there are three problems. The first one is that when you ask a small dot for a hash of something, a small dot cannot get only the hash. A small dot needs to talk with other nodes, get the value, and then compute the hash of that value. So if that value is like really big, then this is like a lost opportunity on bandwidth, right? So the first problem was this one. The second problem, it's a bit like the same thing. Like what this implies is like if you want to know the difference between two different blocks, then you need to get all of the values to compute all of the hashes, to compute the Merkle tree, to see like if two blocks are different. So it's quite hard to see if that's if there has been any differences. And the last problem, which I think that this is the one that makes small dot work a bit slower when dealing with multiple entries, is that there's no way of the node asking for all of the values under one specific node. The only thing it can do, like a node on the Merkle tree, I'm talking. So the only way that small dot can get all of the entries is by asking another node, hey, can you give me the children of this specific node in the Merkle tree? And it's like, yeah, like so the root node has 16 children, and it's those other nodes with these other hashes. And then if small dot is like, okay, now I need to get the values under this specific node, so it makes another request, and there's like a lot of back and forth of like, can you give me the children of this node? Here's the children of this node. Can you give me the children of this node? Here's the children. And then it walks down the tree one by one until it receives all of the values, which is extremely slow because like there's a lot of back and forth, right? So essentially, this RFC, what asked is like, okay, we need like these new data structures and like new kind of request, so that I can now ask for the hashes of specific values, but also for all of the values under one specific tree. So yeah, it was merged 9 months ago, so it's progressing. I don't think it's still implemented though. Okay, we need someone who's brave enough to to make this change in the protocol track, in the protocol repository, and then the small dot can implement this improvement, and small dot will be much better. Yep. So that's it. And now into the challenges that you have when dealing with JSON-RPC. Well, the one that we have seen, right? Like, first of all, correlating messages is not easy. It's not as a simple fetch, which we are very used to it. Like, it's quite hard. So you need like 3 levels of correlating stuff. Like, first, the JSON-RPC message ID, but then also the follow subscription, and then the operation ID. Yeah. So correlating that is not easy. We have this library, which is amazing to correlate messages. And yeah. The other one is handling forks. So this is more like when you want to, request for a storage value. If it's for the finalized block, then it's quite simple. It's like, just give me the storage value of that, and then we're done. But what happens if you ask for the best block, right? If you ask for the storage value of the best block, you can ask, okay, for this specific hash, but then as this value is coming through, now the node is like, oh, you know what? Now the best block is this one. I'm thinking that, because there was another validator that created a node on this fork, I'm thinking that this is going to be the best one. So, when you're dealing with this kind of situations, you need to make a decision of like, okay, what do I do with the value that I just requested? Do I just throw it away? Do I make another request on that? And so on. So that's, essentially like you're dealing with real-time data, basically. So this is something that we will see in another day, but yeah, it's something to keep in mind. Then we have another problem, which is operation inaccessible, which is more or less the same thing. Like sometimes the node is busy and it tells you like, hey, I cannot deal with it. Please come back later. And now you have, like, imagine, right? Like the problem that you have implemented with get body, it was complex enough. Now do it with the actual caveat that the node can tell you like, hey, I cannot get the body for you. Just do it later, and then you have to deal it in there. Then block pinning, that's hard. Like we have not done anything on block pinning with the current setup. Essentially, why is it hard? The thing is that if you're not careful enough and you keep blocks pinned longer than you should, then you will get a stop error, and then you have to recover, and that's not great. So you have to decide, like, when you receive a block, what do you want to do with it? And do you want to keep it for some time? Because maybe like later the user will click on something that, oh, now I need this information of this part of the storage. So I should keep it pinned, I guess. But then if you keep it pinned, then you have to be careful not to forget about it, so that it gets too old. Actually, there's also like another problem, which is like you could have like, you know, you could say like, okay, I want to pin this block, and I keep it pinned, and then the other ones that I'm receiving, I am unpinning them because I don't want to make the light client out of memory, right? So now I'm sure that I will not get the stop error, but that block that was in the past, I want to keep it pinned because I don't know, I'm like comparing values with that block that was in the past. So I still want to use that block. The problem is that the node, light client, will still give you a stop error. Because the fact that you have one block in the past still pinned means that it cannot throw the rest of them, essentially, because it needs to have like continuity. Like the small node essentially cannot have like gaps in between the blocks. So even though you are telling it, I'm not interested in these blocks that are in here in the middle, the small dot cannot just throw them away. So they keep in memory, the memory grows big, and at some point, the small dot is like, hey, I have to shut you down. So the strategy that you use for block pinning, and when you do unpin, it's critical. And the last one is the stop event recovery. So when you receive a stop, you have to think also about this fact, right? Like imagine that you have a storage operation that was ongoing, and now you have received a stop event. What do you do when you receive a stop event? Do you just like cancel that? Like also remember, like a stop event cannot mean anything. Maybe you reconnect again, so you make another subscription, and now you see that the blocks that you have received are the ones that you have in your data structure or whatever. So if you throw an error on the storage request that you were doing, maybe that was not the best option. I don't know if I'm explaining properly. Is it clear by what I mean? So it's like I'm starting a storage request, and this storage request at some point before it gets resolved, I get a stop error, right? In here, I could say like, okay, you know what? I'm just gonna throw an error on this storage, and now the user will see like a big crash on my screen, and because he has been unlucky and so on. But there's like another strategy, which is like, well, hold on, like before making this promise crash and throw an error that everything went bananas because we had a stop error, we can try and subscribe again. So create a new follow subscription and see what blocks come back. So if I see that the blocks that are coming back are essentially the same, or imagine that I asked for the storage of the block number 132, and now when I connect back, the block 132 is still there, then I can still use it, right? So there's a bit of ongoing thing with this. And all of these, again, like the substrate client doesn't really do anything about this. It just like throws the error and that's all, and then it's up for you to recover. But Polkadot API does like a lot of behind the scenes for all of these challenges.